Hello again, everyone. I think we should get started. Again, this is Anita Gupta. Welcome to part one of our pressure vessels fundamental series. And here I take, it's my pleasure to introduce our presenters for today. Nicco Floresca. Nicco Floresca is our Inside Technical Sales Supervisor for Filtration Division at John Brooks Company. Nicco is a graduate of McMaster University with a degree in Chemical Engineering and Biosciences. With several years of filtration applications experience and pressure vessels experience at John Brooks Company, his expertise in both sizing and designing pressure vessels has enabled him to solve many challenges he come across with pressure vessels and filtration applications. Our other presenter is Aniruddha Deoghare. He is the Inside Technical Sales Engineer with our Filtration Division. Ani has over 15 years of work experience with oil and gas companies and with EPCs. His last tenure was the design engineer for pressure vessels for our fabrication shop, which is called MDA Filtration, where he solved many design challenges for pressure vessels while ensuring the design follows ASME code and customers' requirements. And we also have Richard Jacobs with us. Richard is our engineering manager at John Brooks Company Limited, and he's been with the company for 27 years. Richards have been doing ASME Section 8 code reviews for our fabrication shop for the last 9 years, and these designs were approved across Canada. Richard works closely with our pressure vessels design team to review and stamp the CRN packages for submission to various jurisdictions. A little housekeeping before we begin. Note that today's presentation will be recorded and its link will be sent to you as well. Should there be any questions you have, please use the Q&A icon on the Zoom meeting control bar on your screen to submit any questions you might have. We want to respect your time commitment and the 1 hour schedule, so there are any questions still left unanswered. After the 1 hour, we'll address them in a follow-up email to the audience. Again, thank you very much for joining us. For setting aside time, with that, I turn it over to Nicco.
Great, welcome everyone, and thank you to all, and thank you to Anita for the introduction. As there's quite a bit of content to unpack, we're gonna jump right into it. So here's a brief overview of what we'll be covering today. First, we'll go over the definition of a pressure vessel, the fundamental parts, the standards and regulations that govern the design and manufacturing of pressure vessels, the welding component, the testing component, the surface treatment aspect, and then finally, the quality control. And then, as Anita had mentioned, we'll have a question period available as well. All right, so what is a pressure vessel? A broad definition is that it is a container that holds vapors, gases, or liquids at pressures above ambient pressure. They're primarily designed to internal pressure, though they can also be designed to external pressure. And, you know, pressure vessels are ubiquitous in industry. You're going to find them everywhere, really. And to illustrate the types of pressure vessels, we'll be looking into a few examples here. There's certainly many more types of pressure vessels not shown here, so this is just as an example. So the first is a filter vessel, specifically a multi-bag housing for particulate removal. Next, we have a shell and tube heat exchanger. And then the following, we have a air dryer. And for those not familiar with air dryers, the central tenet for plant compressed air is to have that air as dry as possible. And there's multiple reasons for that, but the purpose of the air dryer is to remove any remaining moisture that's in the compressed air. And the next is a air receiver. You know, hopefully when it's installed, it will not be spinning around like this. I don't know if it's still spinning. I don't think it is, but it's something that would be typically found before and after a air dryer. Oh, now it's spinning. And the next is a bank of pressure vessels, and these are media filters. So these can be purposed to hold any types of media, be it carbon, your single grade sand, ion exchange, different resins for metal removal, or they can function as your regular multimedia filter, which is comprised primarily of anthracite, sand, garnet. All right. And then next we have a deaerator, and this is used to remove dissolved gases, primarily for oxygen. And then now we have a general reactor here. You can kind of see the integral jacket on this pressure vessel. And this is used for either introducing heat or removing heat. And you can also see the impellers in case the process may require some agitation. So speaking of reactors, this is something that would be hopefully powering our homes in the near future, a fusion reactor. And John Brooks is not likely to have this within our scope anytime soon, but who knows? And this is actually modeled after a real fusion reactor, in fact, currently being tested by a company called General Fusion in British Columbia. So before we touch on the standards and regulations, we're first going to cover the safety aspect of pressure vessels, because this is of paramount importance, and it does have to be placed at the forefront from start to finish. So to place further emphasis on this, I've pulled a case from OSHA back in November 1985, where there were 3 employees injured. They were burnt as a result of the pressure vessel failure. But ultimately what was found was that the design pressure of the pressure vessel did not coincide with the operating conditions. The steam pressure was found to be 135 psi, but the design pressure of the pressure vessel itself was just under 34 psi. So, in this case, the dots were easy to connect, and the conclusion was that the vessel failure was due to overpressurization. And this is just a solemn reminder that further underlines the importance of having a set of rules and regulations to ensure a sound and safe design. So here again is kind of the steam jacket vessel. So we know that vessels are designed to specific pressures and temperatures. And if you happen to operate outside of these conditions, you will run into the probability of catastrophic failure, possibly injuries or worst case fatalities. And as mentioned prior, we need a set of standards and regulations. And you can see in the adjacent figure here, we have different parts of the process starting from top to bottom. We have the design aspect, the material selection, fabrication, and then inspection. And it's not in a sequential format, it's in a Venn diagram format, because all of these steps interface with one another and they work in tandem to reach the final product. Okay, so on to the standards and regulations. So the most common that you're familiar with is the American Society of Mechanical Engineers, ASME, Boiler and Pressure Vessel Codes, Section 8, Division 1. Now, there's other codes available, such as the European Pressure Vessel Directive. However, in the interest of vessels being installed in North America, we'll be focusing on ASME. Now, it's worth noting that the ASME code is also accepted and utilized in 100 other countries. And the ASME code is quite a substantial document. It's over 700 pages in length. And what this has is a set of rules and formula to design and manufacture pressure vessels. Most companies today would implement software such as Compress or PV Elite to perform these code calculations. So we have the ASME code, but in Canada, we also have the CSA B51 pressure vessel and piping code. So Annie, if you could please shed some light into the difference between the two. To me, and also from a layperson's perspective, it almost sounds like it's the same.
Thanks, Nicco. There are some fundamental differences in ASME codes and CSA codes. ASME codes are used worldwide and provide minimum requirement to design, fabricate, and inspect the pressure vessels. And in Canada, in addition to follow the ASME code, you need to satisfy the requirement stipulated in CSA B51. Well, CSA B51 code provides more rigid definitions and some additional requirement like minimum manhole size or impact testing requirement and so on. Also, to register the pressure vessel design in any province in Canada, to get this Canadian registration number, I'll call it CRN number, you need to follow each jurisdictional requirement such as APSA in Alberta, TSSA in Ontario, technical safety in British Columbia, and likewise so on. There are different interpretations of CSA B51 by different technical authorities. So it's important that you also consult with these technical authorities to what are the differences are and to get the CRN number.
Okay, great. Thank you very much, Annie. So yeah, you can see here the different types of technical authorities available in Canada. And we also have the National Board of Boiler and Pressure Vessel Inspectors. So in this case, the National Board is primarily for the US market. And it should also be noted, because we are following ASME code, the fabricator or shop must possess a ASME certificate of authorization to weld code vessels. And that shop would have to be regularly audited on a regular basis to ensure that they are in compliance with the ASME code. All right, now onto the parts of a pressure vessel. Here's a generic pressure vessel to help identify the main components. So first, we have the shell, and the shell can be either seamless pipe or welded pipe, or rolled plate in this case, that's formed to a cylindrical shell. The next are the heads to close off the vessel. And the following are the nozzles, highlighted yellow here, and for the most part, they can be any connection that provides a means for the fluid to enter or exit the vessel, and also for instrument purposes. And finally, we have your supports, highlighted red. In this case, they are saddles, and they can also be the lifting lugs and the davit assembly for the manway. Now we'll be jumping into the parts and how they're made. So in this case, we're looking at rolled plate in particular because these are more common for large diameter vessels. And how they're made is by putting a plate through a plate roller. You can see in the adjacent photos how they're done. So the plate is inserted to the roller, and with the supervision of the operator, they're going to help guide the process until you eventually form that cylindrical shape. And as with all processes in the fabrication aspect of pressure vessels, there are guidelines within the ASME code. So as mentioned prior, we have the heads, which are used to contain the fluid in the vessel. And there's different types of heads available. You have your hemispherical head, your elliptical head, your F&D head, or a flat head. So the preference is to use heads in most cases because the inherent strength allows the material to be thinner, and therefore you also have less welding, required. And these heads are often referred to as flanged and dished. There's a reason being for that, because the process to make them is the dishing process and the flanging process. So the first process is called the dishing process. And you can see here in the adjacent photo, you have a plate that's under a hydraulic press. And that hydraulic press applies a series of many carefully controlled pressings onto the plate. And then in between each pressing, the press is backed off and the plate is rotated slightly. It could take several hours depending on the material and dimensions of the plate. However, most days they are automatically controlled via CNC, or computer numerical control. Now, onto the flanging process. You can see here the typical arrangement that is required. So in this case, we have two rollers, the first being the drive roller and then the idler roller. The drive roller, you can have two drive rollers. This is the part that applies pressure to help form that head into the shape that you need. And so the reason that we want to do this is to form a straight flange. And essentially, the reason for a straight flange is to ultimately make it easier to weld the head to a shell. Now, into the nozzles. So these are components that penetrate into the shell or head, and the whole nozzle assembly can be considered as the end connection, the pipe, and also the reinforcement if it is used. So here we have a number of codes identified here, depending on the type of nozzle used. And these codes cover the pressure, temperature rating, the material selection, the chemical composition of that flange or fitting, and it has dimensions, tolerances, and markings. And we can also incorporate nozzle loadings per customer request. And you can see another photo here that kind of illustrates the nozzle loadings being applied. So Annie, if you can please provide some guidance on how nozzle loadings are implemented, what impact it may have, and how would we address any deficiencies?
So if the customer asks to apply the nozzle loads, based on the size and rating of the nozzles, if the customer has a nozzle loading table for force and moment in each direction, or we can take the nozzle loading from API 660. So after application of these forces and moment in each direction, you need to check the stresses imposed on the shell and shell to nozzle junction. There is a procedure provided in Welding Research Council, we call it WRC, to find out the stresses. And this can be done by any pressure vessel software to check the local stresses developed after the application of these nozzle loads. And it should be below the allowable stresses. To minimize the stress developed, you may need to increase the nozzle thickness or shell thickness, or you may need to provide the reinforcement pad.
Okay, great. Thank you, Annie. So kind of to go over the figure that we have here again, it is the red components that you see here that can be considered high stress areas, which helps form our decision-making. What can we do to address those high stress areas? So now on to the supports. So these supports are used to bear the filled weight of a pressure vessel. And there are calculations involved, and in terms of supports available, you can use either saddles, legs, skirts, or bracket supports. And supports can be also able to incorporate seismic, wind, and snow loads. Now, these can be more impactful in calculations if the vessel is outdoors and there is significant snowfall. So seismic calcs, not as much, perhaps in specific areas. It could be more important perhaps in BC. However, it is important to note that seismic calcs could be less impactful on support calculations if, say, the vessel is a small vessel or it's short. The taller that you go, the more significant impact seismic calcs could have. And supports are considered to be non-pressurized parts of the pressure vessel. And what this means, it doesn't matter if the vessel is designed for 150 psi or 1200 psi. All that's really considered is the weight of the vessel. And there are other different types of supports available. We have attachment clips for, say, for insulation, your lifting lugs, platforms or catwalks, nameplate brackets or any brackets for that matter, or the closure assemblies. So now that we know what the core parts of what a pressure vessel is comprised of, how do we put it all together? As useful as a duct tape may be, it will not do the job. We need welding, and more specifically, fusion welding. So as mentioned earlier, before you work with a fabricator that welds code vessels, you want to make sure that that shop has an ASME certificate of authorization. And the part of the code that governs the welding component is ASME section 9. And what this relates to is the qualification of welders and welding operators and the procedures that they would employ in welding. So the weld procedure specification, how do we get it? So under this, this is also a procedure qualification record that needs to be qualified, and it's acquired under the guidance of both the shop manager and QA manager. So first, the welder would have to weld the test coupon. Here we have a kind of an example of a weld procedure specification. So let's just use stainless steel to stainless steel as an example. Once the welder uses the weld process of interest and completes the welding of the test coupon, that test coupon is then sent to an accredited testing facility who would test it for both chemical and mechanical properties to ensure that it's within spec and code. And once that's done, it's then sent to the technical authority who would then grant the approval and authorize the shop to use that weld procedure. So there is an expiry date, so to speak, 12 months in fact. And what's typically done to ensure that the procedure qualification record does not expire is the shop would make sure that the welder uses that weld procedure within 6 months. Once they do that, this actually refreshes that procedure qualification record automatically. Now here's a zoom in of the weld procedure specification earlier. So there are pertinent details here, such as the code reference, specifically again, section 9, the welding process. In this case, you see GMAW, which is the fusion welding process, or known as gas metal arc welding, or the slang term MIG welding, and the type of joint welded, and then the thickness of the coupon. And then below that, we have quite a bit more detail, such as the specific material, the thickness range, the orientation of the weld, the preheat temperature, the interpass temperature, and the gas used. So these are all important parameters that needs to be taken into account. And again, this is something that you have to follow code. These values aren't being pulled from thin air. They are in reference to the ASME code. So now that we're done all our welding, we may want to do additional testing. So these will actually be covered in greater detail in the next seminar. So we'll be going over these just briefly. So non-destructive examination, or NDE, can come in varied forms. We have visual inspection, which will be done for all vessels, and depending on the code, design, or customer requirements, you may have other NDE that's required. So just going down the list, we have X-ray, UT, mag particle, hardness testing, and liquid penetrant. So in some instances, the customer requirements may be actually more stringent than code. And finally, we have non-destructive testing. The common one we see and you might see frequently is PMI, positive material identification. And again, just to reiterate, the extent of NDE is usually determined by code, design, or customer requirements. So after we've passed all our testing, stress relieving may be required. And you would know this in advance, either during your code calculations or as a requirement by the customer. Again, this is something that's guided by and covered by the ASME code. So what is the purpose of stress relieving and how and why do we do it? There are stresses induced known as residual stresses from the welding process, and this alters the microstructure of the steel and can be a potential area where the material strength is compromised, so it's important to address it. And we do this by post-weld heat treatment. And you can see here in the photo, it's essentially a large furnace that you would place your vessel into. And there are guidelines within the ASME code that provides parameters for the post-weld heat treatment. And you can also see here where the vessel is stencil painted with the message, heat-treated vessel, do not weld or burn. And this is important because if you do happen to weld or burn the vessel, that vessel has to be sent back for post-weld heat treatment and perhaps other testing is necessary. Otherwise, that vessel is no longer to code. So, Annie, would you please care to add some more comments on the specific instances where post-weld heat treatment is required?
Thanks, Nicco, again. In ASME code, Section 8, Division 1, there are a lot of conditions which causes the post-weld heat treatment to be mandatory. Like in Section UW2, when your service is lethal or it is unfired steam boiler or a vessel is subject to direct firing and the material is your material is carbon steel or low alloy steel. Another one is like the requirement provided in UCS 56 when your nominal thickness exceeds a value of like 1.5 inch for carbon steel material. UCS 56 also provides minimum post-weld heat treatment temperature and the holding time based on your P number and thickness of the material. Finally, UCS 68 also, when your minimum design metal temperature is below -55°F, you need to do mandatorily post-weld heat treatment based on the requirement or even the procedure given in UW40 of ASME Section 8 Division 1. Some customer specification asks for stress relieving based on their service requirement, like a short service or any kind of service if it is required and specified in the specification. You need to do post-weld heat treatment as per the procedure given in ASME code or the procedure given in your customer specification.
Okay, great. Thank you very much, Annie. So you can see here actually a post-weld heat treatment chart that illustrates the rate of heating, the hold temperature, the duration of that temperature hold, and also the rate of cooling. So this is something that you would always see as a part of your package for whenever a vessel is being post-weld heat treated. So before actually discussing hydrostatic testing, I should mention that additional NDE may be required after post-weld heat treatment. There's certain instances in the code that don't require this. For example, X-ray or radiography, it's not required by codes to post-weld heat treatment or to NDE after post-weld heat treatment. If you do it before post-weld heat treatment, you're still in compliance within code. So again, this is something that may be above and beyond the code, it could be a customer requirement. So hydrostatic testing, by code, the test pressure is to be at least 1.3 times the maximum allowable working pressure. You're going to be using water, and there could be situations, in fact, where the client may require the water to have a maximum chloride content. So, you know, normally city water is used to test the vessel. So if that water has a higher chloride content than what is acceptable by the customer, the fabricator would have to bring in water from a third party. And the client would also indicate a specific duration of the hydrostatic test, or rather they could specify a specific duration. Minimum, we would typically test for 30 minutes. And this is a inspection point for any U-stamped vessels. So the technical authority would have to be present during the hydrostatic test. So now we're in the final stretch of pressure vessel manufacturing, which is the surface treatment. We'll be looking at carbon steel specifically right now. So before we paint, you have to prepare the surface. So Annie, if you can please shed some light into the specific parts of the code, if any, that provides guidance on how to prepare the surface. Oh, Annie, I think you're on mute.
Sorry, yeah. So basically, there is no requirement given in ASME code for surface preparation and painting of pressure vessels, but you need to provide some texture on the surface or clean the surface of the pressure vessels as per requirement of coating supplier or your customer specification. For this, Society of Protective Coating and National Association of Corrosion Engineers, we call it NACE, jointly provide the definition of some surface roughness like SP1 to SP14 or NACE 1 to NACE 8. The pressure vessels can be painted internally or externally as per the customer's specified paint or your shop standard with different colors.
Okay, great. Thank you very much, Annie. So again, just to reiterate, the SSPC provides recommendations on the surface prep. So if you prepare the surface correctly, this will ensure optimal paint adhesion, provided also proper paint application is followed. So there are paint testing available. The common one you would run into is dry film thickness. You would hopefully do this in all instances because you want to make sure that the dry film thickness is within the paint spec. So if you have the paint manufacturer saying you need 10 to 14 mils, you want to make sure that that 10 to 14 mils is there around the entirety of all the painted surfaces. So here are the other types of testing available, such as the knife testing, tape testing, scrape testing, and perhaps what's most common is the holodite testing. Now onto the surface treatment for stainless steel in this instance. The story for surface treatment for stainless steel is similar. However, there are different treatments also available. You would likely not be painting the vessels, so you would just have a series of polishing stages. So you can have pickle and passivation, electroponish. You can also have high mechanical polish. And really, it depends on what type of application and service it's being used in. So this is particularly important for any applications deemed as sanitary, or they may be required as they're used in a food and beverage application. So you do not want a rough surface because that's a potential area where contaminants can get trapped, and therefore that process is no longer considered sanitary. So it is important to have that surface polish as required. Okay, now the quality component may be the last in this presentation, but it is by far the most important as it forms the framework for pressure vessel fabrication. And the QA manager is responsible to ensure all steps identified in the ITP are adhered to. And they would also ensure that they are in compliance with the shop QA manual. And just to list a few notable points here in the ITP, this is a sample ITP, the review and acceptance of calculations and drawings, the review and approval of purchase orders to sub-vendors, and then the material inspection and receipt, the welding detail, and then the parts being welded. There's also other items that can be listed, such as whether or not the post-weld heat treatment is being applied, whether or not NDE is being applied. And this ITP is also used as a reference document for the client to confirm, at which stage would they like to consider a hold, inspection, or witness point. Now, onto the material inspection receipt, we'll just be covering this briefly. And you can see here a sample MTR or material test report. And this is what you would receive with the part. So in this case, this is a fitting or a flange in this case. And the QA manager would review the MTR to ensure it's within code. In particular, ASME section 2. And a few items worth noting here is that he or she would verify the heat number, the chemical composition, the mechanical properties, and then those would be referenced against the ASME code and in the adjacent figure you see here. So the quality manager is responsible for accepting that MTR, and once it's approved, it can then be received. Okay, now on to the nameplate details. When it's all said and done, we can now put on the nameplates, and they can be 2 nameplates. The manufacturer's code nameplate is mandatory for all code vessels. And then you can also have the customer nameplate. So you can see here a few pertinent details. So you have your design pressure, temperature, the minimum design metal temperature, serial number, year built, CRN if it is being applied. And then you also have the symbols that are stamped in this little box here, which in this case, the U is indicating that it is a U stamped vessel. The W, it's a welded vessel. And then RT3 is the type of radiography that was used. There are other symbols available. And just to list a few, you can have your national board, post-weld heat treatment, and other radiography and other NDEs. And finally, here we have an index of the history docket or manufacturer's data book. And this would be issued shortly after the vessel is shipped. So this would include other documents such as built drawings, weld maps, weld continuity record, paint report, post-weld heat treatment or chart, and other documents as requested by the client. And now on to, as Anita had mentioned, we do proudly own our own fabrication shop by the name of MDA Filtration. And Anita, if you could please take the reins on this.
Oh, thank you, Nicco. Yeah, you didn't think I could do any much technical. All right, so I'll just talk a little bit about the shop. As you know, John Brooks' company has an ASME certified fabrication shop located in Cambridge, Ontario. And this shop has 30 plus years of experience. I've been building that. So this one shows that what our capabilities are. We have 6 welding stations, about 12,000 pound overhead crane capacity, and actually lately it's higher. So this is older. We can make up to 10 feet diameter vessels and 40 feet length and very high pressure. Nicco has mentioned that we use a welding procedure, which are gas metal arc welding. and gas tungsten arc welding. Our capability in terms of, we are certified to weld carbon steel vessels, stainless steels, aluminum, hastelloy, and duplex steels. I've been building vessels pretty much for all the shipping all across Canada. And I think the next couple of slides, these are just certain examples of our recent shipments. And I believe our shop manager is also online watching that. Must be very proud of this. We are really proud of the quality of work that we produce. So there's some examples of our work that we ship. This is probably the Deoghare and some of the fabricated strainers and bag vessels. I think this was the one titanium vessels we had shipped to a mining company for sulfuric acid filtration. Some multi-bag housings that we build and keep in stock on a regular basis. And of course, this is another type of vessels, coalescers, gas-like coalescers and separators. These are gas scrubbers built not too long ago for our client in Alberta. And some cartridge vessels very commonly used in process industries. We're building regularly at our shop. But more, and of course, multimedia filters, as Nicco had mentioned that multimedia filters means you could put different type of media, sand, ion exchange, carbons. We'll build these vessels and also do complete packages, interconnecting pipings. What else do we have? Oh, these are, talking about interconnecting piping, the shop will not just build the vessels. We will do the complete, the piping design, base plate design, and put them on a base plate and build the vessels around it. And so this explains our capabilities. Now I guess we can go to
the questions. This is actually something that we'll be covering in greater detail as mentioned earlier. The next seminar will be covering specifically parts of the ASME code and compare it to other codes. We'll also be going through a calculation exercise and going into more detail on the NDE, NDT, and destructive testing, as well as supplemental calculations. So with that, we now open the forum to questions.
Yeah,
so
we have some questions. If you don't mind, I'll read them out to you.
Sure.
We have one question that says, can additional nozzles be added to vessel on site to accommodate our piping?
Thank you. So this is something that, because it may be delving into the code aspect, I would actually defer this question to Richard Jacobs, our engineering manager. Oh, hold on.
Richard is, oh, here.
Am I unmuted now?
Yes.
Can you hear me?
Yes.
Okay, so there's sort of like a line in the sand there, and that is depends on whether the nozzle needs reinforcement or not. If the nozzle's less than, now, first of all, I would say it does matter where the vessel is. Am I getting feedback?
Nope, you're good.
Okay. If you are not a competent person, or you don't have a competent person at the site, make sure that your engineering manager knows about the fact that you want to modify a vessel. If the vessel turns out to be a non-code vessel, that means it's low pressure, low temperature, and there is an exemption in your particular province. And exemptions are not the same in all provinces. But anyway, work this through your engineering manager. He will need to know what the size of the nozzle is, what the service of the vessel is, what is in it. Is it cold water or is it some more exotic liquid? Those questions have to be processed. And at the end of that discussion, you can decide, or your engineering manager can decide, whether or not the vessel can be modified on site without contacting the pressure vessel regulator in your province or not. And if the regulator must be contacted, then there will be a repair file opened up, and there will be a notation in the CRN file with an R attached to your CRN number.
Right.
Thank you, Richard.
Thank you.
Yes.
Nicco, we have one more question here. Actually, a few more questions. Can you please explain more about the calculation software itself and what approval does it have?
Okay, thank you, Anita. So in terms of the calculation software, at least within John Brooks, we use the compress, and the formulas, they're all being pulled from the ASME code, and it is something that's generated automatically, though we do need to ensure that the calculations are in fact being done correctly. And in terms of the approval aspect, it is something that most regulatory bodies already are familiar with in terms of the presentation of the calculations. So it's something that as long as it's not adding miscellaneous information that in this case, a surveyor of that technical authority would be reviewing your calculation, you just want to ensure that you're only giving them the relevant information as required by code.
Thank you, Nicco. Another question is, at what pressure does a storage tank becomes a pressure vessel?
Okay, so thank you. So a pressure vessel, again, by definition, is something that that's operating above ambient pressure, or you're also taking into account something with the external pressure being applied. So in this case, if it is a open storage tank vessel, it would not be considered a pressure vessel. It's not something that would be covered, as it does have to be a pressurized unit.
Richard, would
did
you
that
like to
answer
add?
your question?
Am I unmuted?
Yep.
Yes, yes.
It says you are muted by host.
No,
nope.
you're
I hear ya.
unmuted, Richard.
Okay, all right. Basically, John Brooks is in the business of manufacturing metal pressure vessels. So this answer doesn't apply to pressure vessels made from fiberglass, which would be made under Section 10. But a Section 8 vessel, the dividing line is 15 pounds per square inch gauge, 15 psig, which is just greater than a bar metric pressure. So if your vessel is below that pressure, then it does not require registration. If it's above that pressure, then now there may be special exemptions which occur in each province. But if the vessel is operating, if the vessel is a metal pressure vessel and it is operating at greater than 15 psig, then an analysis needs to take place to see whether or not your vessel is exempt from registration in your province.
Thank you, Richard. Nicco, next question is, are you able to help with vessel repairs and re-registering? I think they're saying that is our shop is certified to repair the vessels? Like, do we have the repair ticket? And
Yes, thank you. So we do certainly have the means to proceed with vessel repairs and also re-registering. So it is important to note, however, that whenever you are conducting repairs, again, it may be a requirement to conduct additional NDE again. So it's kind of a cost-benefit analysis depending on the type of vessel that you're repairing. It may be ultimately cheaper to provide a new vessel. So it's something that we would also provide guidance on that regard.
Can I ask Richard here? Richard, with our recent audit there, do we have the repair stem?
I believe so. Yes, we've done repair work recently. I forget the name of the company now, but within the last 3 months, we did a repair job for someone who was between Toronto and London. Yes, and we also, on that job, we did go to TSSA and we did submit a file for the various modifications that were undertaken. And those were all accepted and passed by TSSA, and the repair was completed, and the vessel's been back in service now.
Okay, thank you, Richard.
Thank you.
Nicco, another question, CRNs? Is this requirement of CRN starts with the vessel volume? Is there a certain volume of the vessels calls for CRN registration?
Okay, thank you. So typically for CRN, again, it's something that's governed by CSA B51. And there are decision flow trees which we'll be covering in the next seminar. But the volume that you would typically deal with whenever you have to consider CRN registration, I believe it to be 1.5 cubic feet. Richard, if you can please verify.
You are unmuted by host. Okay, so I think we would want to first of all say that the volume of the vessel is not the only factor to be considered. There's a number of factors to be considered, and it may be that a pressurized entity which is smaller than 1.5 cubic feet may require registration as a fitting. So volume is one consideration, but it's not the only consideration. But generally, Nicco, you are correct. Above 1.5 cubic feet, we start looking at pressurized enclosures as vessels rather than as fittings.
Thank you, Richard. Thank you, Nicco. There's a question here, Richard, and I'll direct it to you. What is the definition of full vacuum design for pressure vessel?
Well, I would, that full vacuum design, I believe, is not a code definition. This would be a definition of the designer or the customer, but what's going to happen is, I mean, it would be very unusual for your vacuum equipment to be able to achieve absolute full vacuum. So your vacuum pump may be able to achieve something which is close to full vacuum. If we are at sea level, then atmospheric pressure is 14.7 pounds per square inch gauge. So your vacuum equipment may be able to achieve say minus 13.5 psig. But for convenience, it is likely that when you design your vessel, it's just easier to design it for minus 14.7 psig because the difference in material thickness between minus 13.5 and minus 14.7 would be negligible. So I would say for convenience, I would use minus 14.7 psig.
Thank you, Richard. There are two more questions which were sent before.
Okay.
One was, can your design engineer help with seismic load calculations? And also, can your fabrication shop build the vessels as per site seismic requirement?
Am I unmuted?
Yes, you are, Richard.
Okay, so with seismic, Brooks has done a fairly large number of seismic calculations. So this will occur where the vessel is being installed in an area with seismic requirements. In Canada, we refer to the National Building Code of Canada, and their procedure is fairly well defined. So we have used it a number of times. Now we cannot do this for nothing that involves engineering time and computer time to do these calculations. But for your money, you will receive a P.Eng stamped set of calculations for your particular province.
Thank you, Richard. There's one more question that had come in advance. With the calculation software, does it advise when a vessels need post-weld heat treatment? Or is it a client's request when post-weld heat treatment is done?
You're still asking me?
Yes, please.
Okay. I'll have to say I'm hazy on that as to what Compress will do. As a rule, we would not leave it to the software to decide whether or not post-weld heat treatment is required. When we review the drawings before they go into the regulator, we'll be considering post-weld heat treatment much as we do other things like radiography and mag particle. What is the customer specified in terms of quality control? What has the customer not specified? But what should John Brooks and MDA follow as good practice? And I can tell you that our shop people are very aware of situations like this. And if we were ever to forget, the shop people would quickly send us an email on the subject of post-weld heat treatment.
Thank you. Nicco and Annie, would you like to add anything? Or actually, these were our last questions.
Yeah, so our complex software provides when the thickness of the gardening thickness is more than 1.5 inch for shell. So it gives the requirement of post-weld heat treatment. And the software, the complex software itself is totally follows the ASME Section Division 1 or Division 2 code. So once the thickness exceeds this gardening thickness, it automatically provides the post-weld heat treatment is required for this particular vessel.
Thank you, Annie. I guess this will be on the last slide. The email addresses and the phone numbers are there. If you have any further questions, please feel free to forward this to Nicco Floresca or Aniruddha Deoghare, or you could also reach us by our main number. Again, thank you very much for joining us, and we will just stay tuned for our next seminar. Thank you again, everybody. We'll see you next time.
Thanks, everyone. Take care now.